Welcome. Thank you guys for joining me today at NGINX Comp. I'm here to talk about dynamic load balancing and deployments with NGINX and Zookeeper. I'm here to tell you why you should invest in your traffic controller and talk about the heart of the systems that I build in my everyday work life. So, first of all, who am I? This thing doesn't work. Great. That's why. All right. So, my name's Derek DeYoungie. I'm a cloud solutions architect and NGINX enthusiast. So much so that my advocacy has made NGINX our default go-to for web serving and proxy in my organization. I'm certified by AWS, and I work for a company called Right Brain Networks. We are an advanced consulting partner and managed service provider for AWS and Azure. We help companies migrate into AWS, revolutionize their workflow by bringing in CI/CD and infrastructure as code, as in infrastructure management and configuration management. So we typically deal with SaaS systems, services that are provided to the world, etc. I'm also in embedded consulting roles with larger organizations, as well as running lots of systems for smaller organizations. So today, we're going to have a few topics. We're going to briefly cover some reasons why we're doing things like this. We're going to talk about who our actors are and what our goals are. We're going to cover some basic cloud concepts and DevOps. And then we're going to talk about what I mean when I talk about dynamic load balancing. We're going to explain some of the obstacles around microservices and autoscaling, distributed architecture. I'll detail some of the processes around releasing code and what that means in dynamic infrastructure and how NGINX and service discovery can be utilized to impact these solutions that we can. So who are my actors? My actors are your end user, right? When we deploy code, we want to make sure that they get the best performance and the best, But, all right. So what do our users want? They want zero downtime. They don't want to have to wait for a maintenance mode for new features or bug fixes. And they certainly don't want mail-formed requests. Our other actors are the teams that are developing the software. They want to spend less time deploying. They want less effort for deploying. They want to spend their time doing what they do best, and that's developing and moving forward with the product. So what are our goals here? We want to automate live index and code deployments. We want to update things more often. We want to, we want to eliminate the need for lengthy deployments, the resources around those deployments. Have you guys ever seen a war room set up, stacked to the brim with snacks and people sitting there for 36 hours straight? Right? We need to get away from that. We want to eliminate the need for overcapacity of data centers. And we want zero service disruption. And we want to make sure that every request is sent to the right application server and the right version. And we also want dynamic load balancing. Because in my world, everything's built in the cloud. That might not be how everybody else is here. but this is a problem that I have to solve day in and day out. So let's cover a few cloud and DevOps concepts. Everybody here is brilliant individuals, so this might be wasted, but with the drive to the cloud, a lot of companies are decoupling their monolithic application servers and going with microservices. And this concept makes many different distributed services that all work together to provide your service or product. Microservices allow you to scale on a very granular level, which saves on cost and allows people to, developers to get their work done more cleanly and push it out more efficiently. So, with that, microservices is a great thing. I mean, with cloud, cloud and microservices go together like engineers and coffee. Engineer might not actually need their coffee, but they work a little bit better with it. So, the same idea with cloud and microservices. So, being able to scale at that granular level, just saying, okay, we're getting a lot of authentication requests. We need to scale up our auth portion of the application rather than, some worker on the back end that might not be under such load. So, this microservices definitely causes a little bit of complexity when you're deploying and in your environment as a whole. So let's take a look at a pretty simple architecture and what it might look like to for a packet to run through this. We have a request, hits our web layer, back to NGINX, goes to our API layer, and then finally to our data. It's important to note that the data that I'm talking about in this particular example are Solr shards. They're immutable, they're static data, and we've got multiple shards, multiple replications of that shard, etc. So, with that, our packet travels back out through the stack, back to the end user. You can see how much more complicated this can get if we add another service, or 10 services. Deploying to these is going to be a little bit more complex when you want to offer that zero downtime, high availability. So, what's the idea there? Continuous delivery. You'll probably hear it day in and day out for the rest of the conference, but continuous delivery is a completely automated system. It allows you to spend less time doing release work, increases your productivity, and ensures for reliable releases. It decreases your time to market for things like new features, bugs, etc. And that improves your product quality. It increases your customer satisfaction because you're squashing those bugs, you're releasing those new features faster. You don't have to wait for deploy time where we have to put up that war room and there's tons of people. Man hours spent time deploying. And it gives you more time to focus on what really matters, moving forward with your product. So another concept of this continual deployment, zero downtime, etc., is the Bluegreen deployment. It's one of the most sought after deployment styles of today. This deployment style allows you to seamlessly direct traffic to a new version of the application code running on separate sets of infrastructure. The fulcrum of these deployments is the traffic router. Whether it be DNS or something like a proxy with NGINX, these deployments offer zero downtime and the ability to switch back to the older version if things go wrong. This lowers the stress of the engineering team and increases your, again, customer satisfaction. You have zero downtime, and that's exactly what we're looking for, right? So this is a quick diagram of what Bluegreen might look like. You have application version 1.0, application 2 spins up, you switch traffic, and the old version goes away. Same idea with, say, NGINX. But the idea here is that NGINX is able to do this a lot more cleanly than DNS because we don't have to wait for things like TTL. There's a lot of inconsistency around that. You don't know exactly when things are going to switch, what application servers are going to switch at what time, etc. So this is why doing it with NGINX is the preferred way for me. Auto-scaling, we'll just cover this briefly because it does present a lot of problems, and while it solves quite a few as well. So, some of these obstacles when you're scaling horizontally to increase your performance under load, things to that effect, you're going to have very dynamic backend and infrastructure. Your deployment has to change. It's not SSHing into boxes and swapping out code or just git pulling anymore. Things are vastly different. So, this is one of the problems that we've been trying to tackle, is being able to load balance dynamically. This means when we have servers spin up, we want to make sure that they get put into the backend pool. We want to make sure that, if they die or scale down, they're removed from the backend pool. And with products like the Elastic Load Balancer or NGINX Plus, that's solved for us, right? Instances come up, they check into NGINX, and NGINX starts passing traffic to them. So why NGINX, right? Being that we're at an NGINX conference, I hope I don't have to convince any of you, but let's talk about why not the Elastic Load Balancer real quick. So this Elastic Load Balancer offers a lot of great things like that dynamic load balancing where your instance comes up, it checks in, it starts getting past traffic. But there we go. All right. So that solves a lot of problems for a lot of teams. It's a really great product and it does what it does very well. However, we have some problems here, like only a single backend pool, no context switching. And one of the biggest pains is that once a instance registers, it has a minimum of 4 seconds before it will start being passed traffic. This is because of the health check, right? It has to pass 2 health checks, and the interval must be 2 seconds or more. With that's a huge issue when trying to use an Elastic Load Balancer for dynamically switching out versions, unless you're doing something like DNS to point to a different load balancer, which again, we come back to the issue of TTL issues and DNS caching. The need for a more sophisticated deployment and traffic router is greatly increased by the use of microservices. Because we want to be able to do the context switching, we want to be able to have dynamic load balancing, and we need to be able to do deployments. So NGINX, like I said, hopefully we don't have to convince any of you guys, but for me, NGINX is this perfect Venn diagram here. Equal parts rocket ship and bicycle. High speed and low resource footprint. It's scalable and highly configurable. The Lua aspect of this allows us to do so much header manipulation that we can really do whatever we need to. The other part is the seamless reload. This is a feature that a lot of other proxies are missing. We're able to do decision making, context switching, routing these requests to exactly where they need to go seamlessly. So let's move on to the interesting stuff. Everybody here knows about NGINX, but how does service discovery fit into this? Now I'm going to talk about Zookeeper, and a lot of people here are probably asking, why not console? Well, the answer is I'm a consultant. I get put into larger organizations, and I don't always get to make all the technology decisions. In this particular case, the team was moving towards Solar Cloud and wanted to implement Zookeeper so that they were ready for that. Zookeeper is a centralized configuration store. This is where you might store all of your metadata about a server, all of its roles, all of its data models that it's running, things to that effect. Zookeeper clusters and scales really nicely. It's a pub subsystem, so that means that we're not only able to push data to it and pull data out of it, but you're able to subscribe to different events within the system and register callbacks to be had when something, an event takes place or changes in the system or data are presented. All of the services in the environment are always connected to the Zookeeper. If a node falls off the face of the earth, the connection's dropped, and that node is no longer in connection to the Zookeeper. So with that, we have really what I'm talking about here is the socket between the two. So things are really fast. There's not a connection being opened and closed and opened and closed. We're always connected. And it's really fast, millisecond fast. And that makes the ability to scale and have this dynamic to your environment really speedy and graceful. So Z nodes are what the data is actually called. It's a blob of any data limited to 1 megabyte. But these Z nodes are stored in a very Unix-like directory structure, which is pretty comfortable for most people. You have child and parent nodes. The parent node can actually hold data as the child node can as well. So let's take a look at a Z node example. Let's go ahead and get the root. We have a few things. We have a few Z nodes here. API, web, NGINX. So let's take a look at what NGINX is holding for us. Here in my example, I listed out a unique identifier. So these are all of my NGINX nodes that are currently running connected to the system. Let's go ahead and ask for the data within one of those nodes. And here we'll see things like IP, release version, things to that effect. So how do these systems work together? You guys like diagrams, right? Great, I do too. So here we're going to stand up Zookeeper. We're going to build our NGINX boxes. NGINX will check into Zookeeper. We've got our web layer. Again, checks into Zookeeper. However, here we have the NGINX box has a subscribe to the web layer Z nodes. So this event is pushed out to the NGINX boxes. NGINX Client will know what to do with that information and template its configuration accordingly. Same goes for the API layer and the data layer. So let's talk about this node client. What are we doing here? We're grabbing data, anything I can find about myself. We're doing self-discovery. We're going ahead and putting that into a Z node structure that's based on things like the environment it's running in, the role of the application, and then finally a unique identifier. These can be built in very modular ways. For instance, most of my node clients were very common. All they needed to do is just dump data into the system so that NGINX could find it and act accordingly. The information we put in here is actually pretty important. Now, we want to be able to know exactly what the IP is and definitely the release. This is going to build as we get further into exactly what's happening with the deployment. You can really put anything pertinent into it. Same things you might find in environment variables, things to that effect. Given that that discovery, the Z node will be, the node will be able to construct the Z node path in a meaningful way, and with that, we'll have something that looks something like this. We have what we call ephemeral nodes inside of this structure, meaning that if the connection is ever severed between the node and the Zookeeper, that node will then disappear, which means that we don't have to clean up after ourselves. It's done for us. And if there's ever a blip in connectivity, then we're no longer routing traffic to that host. I decided to store my my configuration data in JSON format because it's independent of languages. I was using an orchestrator written in Ruby, and all my nodes were in Python, so it made it a very common language to be able to communicate across. So let's talk about the NGINX Client. The NGINX Client provides all of your functionality and decision making. The NGINX Client might do the same things that the Node Client will by importing, putting its data into Zookeeper, setting up the structure. However, one thing that it's going to do differently is that it's going to subscribe to different nodes and different parent nodes in the Zookeeper directories. This client would also ask questions, getting information about the different services in the environment so that it's able to template its configuration and make changes accordingly. This is done via templating and configuration files. My NGINX client included the templates for these different configuration files. Things like templates of pools, variable changes, mappings, and even being able to produce full servers, right? So I talked about my data example being solar. Now, running a solar cluster, you might have 2 nodes, you might have 10 nodes. Your dev environment might have 10 nodes, and your prod environment might have 200. Setting up the NGINX rules for those is boring. Nobody wants to do that. So with this, we're able to dynamically find out how many shards are there and template out all of the servers so that we're able to not have to type all that out, and it just dynamically generates all of the services. The NGINX client might want to know things about health for all those boxes. If something's not acting appropriately or serving requests appropriately, you know, they can do health checks on the local node, put that into Zookeeper and say, hey, I'm healthy, pass me traffic, or you know what, we're getting 500s over here, don't send me any more traffic, we need to figure this stuff out. It also wants to know when things register to the system and when things disappear from the system. That gives us the ability to template out those pools very efficiently. You can also do things like, I was kicking around the idea of load. If you have an API that takes large data sets, small data sets, and one's really cranking away at things, you know, you can say, you know, this server's under a lot of load. Let's send less requests to this, point them to somewhere else. The NGINX will register callbacks around all of these different parent or child nodes that they're subscribed to, and that callback is going to work appropriately to reconfigure its configuration. And this right here is our dynamic load balancing. So let's talk about the upstream pools. So the pools are created dynamically based on the Z nodes in the environment. Instances are pooled by application and version. That's something that is a little bit different, I would say. We're not really load balancing over the service or number of servers, but really what we're doing is we're load balancing over the application version and the application. All the upstream services must pass health checks, etc. So here's a little bit of pseudocode on templating this out. Very, very simple. You can also put port in there. You can see how this might drop into something like a containerized environment. And we'll end up with something like this. So our requests. What happens when a request comes into our system? It's going to take that natural flow, moving through the application stack, and then being popped back out to the user. So here we're doing context switching on, what's the host name I was provided. Okay, we're going to go to this particular application. And also, we're going to take a look at the request and what version it's bound for. So, what happens? Where am I? So the version header is mapped to the application pool by different versions of this application that we're load balancing over. And we're going to route that traffic appropriately. So here's a map of, say, what the request version might be for a particular request and direct it to a pool so that we're able to proxy this request to a particular pool based on not only the application but the version as well. So this is the meat of it, how our deploys really work. A new server is built, health checks are passed, NGINX templates the pools, then orchestration might change the NGINX version by making an alteration to the NGINX Z node. The NGINX client is actually watching its own Z node for changes so that an outside force can actually change its version. At that point, NGINX will go ahead and retemplate its configuration saying that my current release version is 1.2.4, where the previous version might be 1.2.3. This is actually pretty important because of how the request actually gets tagged. The request is tagged if it doesn't have a version within the system. That request will flow through the different services tagged with a particular release. As the client notices a change to NGINX's release version, it goes ahead and retemplates its configuration and directs traffic to the newest version for any new request. Now, what happens when you have a request that's in mid-flight between all these different microservices? You just switch versions on it. That seamless switch for the Bluegreen is great in theory, but if you have a coupled service that is making a request to a version that it's expecting to reply it in a certain way, and you switch its version, it gets a different reply, you're going to have a malformed request. And that's the issue we're trying to solve here. All right, so a typical request might be going through the system, and we will see new boxes built, but where is it? My image just got messed up, I'm sorry. The idea here is that if we were to build services in the middle of a microservice request, that it might end up going to the wrong node. We don't want that to happen. So if we switch versions, even though NGINX is on a newer version, we're able to direct the request to the 1.2 version appropriately. The outcome here is that we're highly available. We don't have any maintenance windows. We have zero downtime, zero malformed requests. We update our data and our code more frequently, faster, and of course with less headaches. Effectively turning deploys from something like this into something more like this. The impact is higher customer satisfaction, higher engineer satisfaction, higher productivity, and a better product. Thank you. My name, again, is Derek DeYoungie. Work for Right Brain Networks. Suppose we got a few moments here for questions. Wasn't quite prepared for that, but certainly. No, there's an external process that's continually running. It's a daemon that keeps an eye on all these things. It'll go ahead and reload. Yeah, exactly. Not at the moment. It was built for a particular company. The idea is mine. It's their code. The client actually has a built-in, and the Python library for Zookeeper is called Kazoo. It's actually got a really nice retry mechanism that will, if there is a severed connection or timeouts, there's different things that you can do to take the appropriate step to reconnect. Yeah, absolutely. If it can't talk to Zookeeper, it's not going to retemplate its configuration. No more? Yeah, the idea here is that, you know, if you're running microservices, you may have upwards of 30 different services in your environment for your product offering or service. And to be able to do that with ELBs, you're going to need to run 30 ELBs. And that's a huge waste of cost. It's harder to work with and work around. So the idea would be to replace all those multiple ELBs with a system that is dynamic and does context switching over multiple pools, different application services, and versions. So that is through the pub subsystem, publish and subscribe, right? So this is an idea where you can tell Zookeeper, I want to get updates about any event to any of these Z nodes. And that actually sends a message back to the client, and the client has a callback function that runs and does that.
So the client is actually inside the NGINX?
Yes. So it's a small client that runs on each node, right? The first one is really just the node client is there on each node. Doesn't matter what services it is. It's just sitting there, you know, at any interval you want. It'll just check its health and make sure things are appropriately, you know, send information back if anything's changed. When something does change, Zookeeper will notify the client on the NGINX boxes, all of them.
That client is the Python client?
Yeah. Yep. Any other questions? Oh. So what I would say to that question is that Puppet, Chef, SaltStack is our go-to. Those are used to set things up, right? They're used to configure the NGINX box and set up the client, and they're used to set up the NGINX nodes and cluster them, things to that effect. If you were to run something like this with Chef or Puppet, my feeling is that it might be a little bit slower and might be a little bit more engineering work to kind of do that discovery and figure out what's going on and route things appropriately. It's definitely doable, absolutely doable. But with service discovery, the pub sub is really what makes things fast and reliable. Where, you know, I know Chef is moving towards a push-pull model. Salt's already there. I'm not entirely sure about Puppet, but you know, having that subscribe is really what makes this a big difference. All right.
One last question. How do you handle Zookeeper buckets? Like, do you add listen to all of them? Or?
Zookeeper clusters.
Yeah.
Yeah, so you can connect to any number of them, and they all have the same information, and they have chatter or gossip between them, and they're just in a cluster together. I think there is a little bit of work to be done around actually having scaling Zookeeper, the clustering itself. Netflix has an open source product that does it for you. I think it's called Excalibur or Exhibitor. That's right. Any other questions? Great. Thank you guys for coming and listening to me talk.